Okay, so if we take a look at this problem here, it says find the linear approximation of the following function f at the x value and use it to approximate the function. So I'm looking for an answer of what is f of 2.5. Now, if I had a calculator, I could plug in 2.5 into these two pieces and then figure out the answer, and that would give me the exact value. But they're asking us to use the linear approximation, which is the tangent line. So what do we need? We need a point and we need a slope. Actually, rewriting this, we can think of what do those pieces mean, right? What is your slope? Well, the slope is the derivative of this function at x equals 2. So I got to find f prime of 2. And then I have to find the other two pieces, which is x1 and y1. Well, they tell me what x is equal to here. X is equal to 2. And then I can find what the output is at regular 2. So I need to basically find the slope and the point. It doesn't matter which one you start with. I'm going to start with just the regular point. Now again, our whole idea is to do this without a calculator. So we know what f of 2 is. That's equal to 4. So I found my point. Now I have to find the slope, and the slope is just based off of the derivative. So we're going to take the derivative of the original function, which is just 2x minus 6, and then I have to find that slope at the given point x. Okay. So what do we have? We have the equation y minus, I'll try to use my colors here. What is the output? We found the output was 4. What was the slope? We just found the slope at negative 2. And then what is the input? That was when x was equal to 2. So you can simplify this, and I'm going to do it this way. I'm not going to distribute the negative 2. And then this 4, I'm just going to put plus 4 at the end. And then instead of calling it y, remember y and f of x are the same thing. So here is the equation of the tangent line to this curve exactly at 2. But then they're telling us to use this equation of the tangent line at 2.5 to approximate, and I should be careful with my equal sign. We want to roughly estimate what is the slope, or excuse me, what is the value of the original function when x is 2.5. So it looks like a lot, but we just found the equation of the tangent line, and we're going to use that to evaluate this function. And the nice thing is I get 0.5. The reason why we don't distribute is it's usually friendlier to just leave it and then simplify as you go. Because if I take half of negative 2, negative 1, and we get 3. So that is the approximation. If I plugged in 2.5, I'll get something close to 3, but it won't be the actual, it probably won't be exact. Really quick, let's think of visually, what did we just do? And I'm not 100% sure what this parabola looks like in terms of if it's more on the left or more on the right. I think it's going to go something like this. I know it opens up. I know it has a y-intercept of 12. And then what did we find? Right? What was this part right here? This was the equation of the tangent line at 2. So at 2, we found a tangent line right here. Right? And then what did we do? We went over to 2.5. This is not going to be very accurate, but I went over a little bit. And instead of being the actual answer on the parabola, I used the tangent line right here to figure out what the output was. And I said 2.5 is equal to 3. So we found that in that video we watched last Wednesday, that you can use the tangent line to approximate values that are close to the x value that you found the tangent line for. And that's all this is. Now there is one other connection here that we could make. Notice our estimated answer on the tangent line is going to be less than the actual answer on the parabola. And the reason why is the parabola is what we're going to call concave up, but the tangent line is below the original function. Okay? What I want you to do is I want you to grab your calculator right now. What we're going to do is, I kind of mentioned this last week, but we're not going to officially teach 4.1 because we've already talked about it and you guys kind of already know how to do it. My goal today is how do you use your calculator to find derivatives? So, hopefully you have some type of graphing calculator with you, and hopefully it's a TI-83 or a TI-84. If you don't have a graphing calculator and you have a school Chromebook, there is a icon on your desktop. If you just go to your blank screen, look for the icon that says TI-84 Smart View. I think it says Smart View on it. And what I'd like you to do is open that up. If that doesn't work, I'm going to see if I can send a link in the chat here to a calculator that looks like this. And it's basically in a program that you could use. And this one actually might even be more friendly than the one on your computer. All right. I'm not positive if this link is going to work for you. I know if you click it, when you click on it, you have to click through, and I think there's a start button. It's basically a practice test that you're opening, but it's going to get you this calculator simulator. So once you click on that link in the chat, you have to click on the TI-84 graphing calculator button in the top kind of center part of the screen there, and then this should pop up. Okay. Well, either way, if you have your own calculator or you're using the one on your Chromebook or you're using the link that I just sent you, we want to go through this really quick and kind of help you out. So, what if I gave you a problem like this and you were allowed to use your calculator? That means I don't need to see any work from you, and it's meant to really save some time. So, let's look at this. The number of fish in a pond is given by the equation P of T. In a federal wild reserve, after 2 years, the population is given by P of T, which is 60 divided by 1 plus 19 e to the negative 0.2 t. So there's a function that models the population of fish over t years. Well, the first thing we want to do is explain the meaning of this limit. So you don't need to do anything. Now you could do this. You could plug infinity in here. And I might just show you this one really quick just so you see what this would look like. If I evaluated the limit and I just plug in infinity, right in for t, I put infinity. Well, what happens then is this whole part right here really becomes e to the negative infinity, which we saw the other day that's basically 0. So e to the infinity turns into 0, and 0 times 19 is 0, which gives me 60. So what does that mean in the context? Our population of fish is 60 fish at t equals 0 years. So it's basically saying, oh, I'm sorry, not right. I was thinking about an initial value problem. Um, This is not at zero. This is when t goes to infinity. So we know that the population of fish is 60, or let me phrase that even better. The population of fish has a max of 60 fish. It's not going to go higher than that as t, or in this case x, goes to infinity. So let's take a look at this. And what I want to do is just graph it for right now. Oops, wrong button. So you're going to go to your calculator and enter this into y equals. And I want to show you something that works on most TI-83s and 84s. I think this is super helpful. If you do alpha y equals, so that's the green button, and y equals. And what that does is that pops up this n/d. That's a numerator denominator. It allows you to put this in as a fraction. So then I'm just going to type in the equation. And I am making a small assumption that from pre-calculus, you guys know where the E button is. If not, it's second ln. All right. Now, it's important to note that we put this in as y equals. So I'm going to hit graph, and I'm probably going to have to change my window. Actually, I might even do zoom fit. That's option 0. So zoom fit. And that shows me an exponential graph. But there's something more interesting about this, and it's kind of important for you guys to understand where and how this works. I definitely want to see x is my time. I want to see more than 10 years. I'm going to see what 50 years looks like. And then I always do like a -10 to, and then my answer algebraically went up to 60. So I might just type 80 in for the y max. And I might be going a little fast here. You don't technically need everything that I just showed you here. But what I just did was I just graphed more of this function further in the x and further in the y maximum values. And notice this graph looked like it was going to just increase forever. But then when I changed my window, it actually started to flatten out. And that flattening out point, if we were to just trace it, you can see the y values are going to get closer and closer and closer to 60. Here I'm at 59.9. Because this is a horizontal asymptote, it will never cross 60, but that means that as time goes on forever, the most amount of fish that will be in this wildlife preserve is 60 fish. So that's just a little visual evidence of what we're doing. But now let's look at part 2. Okay? And this is the part where you definitely want to make sure you're with me. And if you need me to, I can go back over some things. All right. Number 2 says, how fast is the population growing at 2.5 years? Well, what are they asking? They're asking for a rate of change. Well, what is the rate of change of a function? It's the derivative. All right. So the derivative at a specific time. I need to find what is the derivative at 2.5. So the first time I tried to show you this on last week, but my graphing calculator simulator froze up, so we actually never got to this. So I'm going to show you 2 ways to do this right now. The first one is, what if you have a graph already? Well, as you hopefully remember from all your years in math, second trace gives me the calculate function. And if you scroll through it, hopefully you know how to do zeros, values, minimums, maximums. But the part you want to look at is look at options 6 and 7. dy dx, that stands for derivative. And you don't know what this notation is for 7, but we're going to use this later on. This is the integral symbol. But look at option 6. It says, find the derivative? Sure. Hit enter. And then here's the part. It doesn't really prompt you anything except for it says calc derivative at a point. Well, yes, and I want it to be at the point 2.5. So all I did was go second calc, option 6, and then I typed in the value that I want. And you'll notice something. It gives me the derivative exactly at that point. Let's see. So you can see right here, dy dx is equal to 0.8816419. It gives me the derivative at the given point, which, by the way, if I ever really wanted to, since they gave me both a derivative and a point, you could write the equation of the tangent line if you wanted. But all we're concerned about right now is the derivative. So what is the rate of change at 2.5 years? We have 0.88616, but that 1 should really round up to a 2. So this is one way to find the derivative if you have a graph. And then we also want to include units. What are the units on this? Well, this is the change in the fish population, right? That's what the outputs are per time limit, which is year. So this would be, we are growing at 0.882 fish per year. Okay, let me show you another way to do this. And here's the nice thing. Making it bigger really doesn't help. So here's what we're going to do. Go to y equals, and I want you to note what is in here is y1. Right? I'm going to show you a way that could be very quick. If you have this function typed into your equation, then you don't have to type it again. We can always refer back to it as y1. And then go to a blank screen right now. So go second quit, which is the mode function, and you're just at a blank screen. Okay. This option is really friendly if all you want to do is find the answer and you don't really care about what the graph looks like. So the third button, well, on the left-hand side, there's the math button. It's right below the alpha. If you click on math, we're going to scroll down to option 8. Okay, option 8 says n-deriv. That means for a derivative out of a value. So it's going to find the numerical derivative, and it only finds the answer at a point. This won't just like take a derivative and give you the equation. It only gives you the answer. But select option 8. And now here's where it differs. And this is where if you're using the TI-84, which everybody that has a school Chromebook should, or if you use the link that I sent in the chat, that's the one you want to use. If you use your handheld calculator, it might not be in this format. So I would recommend using the one that has this format. All right, notice it says d over d something. Well, we always want dx, so you're going to hit the variable x. And then this is the equation that you could type in, and you could type it in just like this, or here's the part you really got to pay attention to. We already put it into y equals. So look at the button that says vars, V-A-R-S. It's right next to the clear button. And then if I go over to y vars up top, so hit the vars and press over to the right, and your first option under y vars is function. You hit enter, it's going to take whatever you have in y1 or y2 or whichever ones you want. Well, we want y1. So select y1. And that's going to take the place of this equation that we had before. So it's really nice, meaning you only have to type it in once. And then we have the bar, and so it's basically saying you want the derivative of the function you put in y1 at the point, and we're doing number 2. I want to put 2.5 as the value that I'm looking to find. And then hit enter. And notice it gave us the exact same answer as the method that we found on our graph. So I know though that was the first time you saw it, and we're going to, anytime we can, we're going to make use of this, but that's a real quick way of doing this.
How did you get the Y1 in there?
Okay, I'll show you again, and I'll actually show you with the second problem that we'll do here. So now look at this next question. It says, how fast is the population growing at 30 years? So it's the same question, it's just now we're using 30 instead of 2.5. So here's what I would do. Let's say we start from a blank screen. All right, you're going to go to the math button, and it's going to be the 8th option. You could just press the number 8. That's n derivative. Then we have to hit x because it's d over dx. It will always be x. Even though our variable is t in the original problem, our calculator just needs to call it x. So, all right, now here's the part Ian that you just asked. How do we get the equation in here? Well, because it's the same equation we used in the other problem, that equation was logged into y1. So here's how you get it in there. The vars button right here, it's kind of right next to the clear button. Click vars, and then you have to scroll over to y vars. And it's your first option is function, and hit enter. And then there's the y1. If let's say you forget where that is on a test and you want to use this, then all you do is instead of where the y1 is, take the original equation that was given and just type it in there. So now we want to figure out how fast is the rate changing at 30 years, or another way to say that is what's the derivative of the given function at 30. So type in 30, and there it is. All right, so hopefully you will make use of this when necessary. Um, and try it again right now. I'm just going to fill this in my paper, but try it again for 100 years. I want you to see what our answer to how our answer to number 1 is playing out. And if you can, try it again for 1,000 years and just see what happens as it's growing. All right. I'm also going to let you in on a little secret. So what if I want to do this again and again, and they ask me to keep doing it, which they really won't. But I don't know if you guys know this. So what happens if I go second, enter? Notice how it started off with exactly what I just had. Um, this does work with the T83, except for the notation looks different, and it's a lot trickier. I can show you that in 1 second here. So let me just kind of finish this. So what did I do? Instead of going through the same steps over and over again, I just went second, enter, and it took what I previously put in. And then all I have to do is press the back button and type in 100. Now notice we're getting scientific notation, which just means I'm moving this decimal spot to the left 7 spots, which basically means this rate, as I get further and further and further, like let's do like 10,000. So what's the population of fish after 10,000 years? I should say, what's the rate of change? Notice how it basically gets to zero. That's what this middle one was. It's a scientific notation that basically is zero. Well, does that make sense with our curve? All right. Look at the graph of our curve. The slopes, as I get further and further to the left, the slopes are going to basically be flat, which means there's no change. The slope is basically zero. All right, we're not going to do the bonus. This is something that was, ooh, the bonus was something that was, if we had time, we're going to really cover it next unit, so we don't need that one. I'm not positive if the TI-83 is going to, if it's going to do this. I want to try one thing here. I just found out from, you guys don't have to write this. Okay, so here's the thing. If you have a TI-83, all right, notice how my notation changed here. What you have to do is you have to go second math, and you'll get the end derivative just like we did. And then you have to put in y1 the same way we did on this one. And then you have to do comma x comma your number. And I can show you that in more detail. My recommendation right now is use either the link that I sent you or to use the link on your Chromebook. So that way everybody has a TI-84 because it's much friendlier. And if you mess up this order, it's not going to work right. So if you want to stick to your TI-83, I can spend some more time later on and help you to do that. But using the TI-84, it just has this much friendlier mode. All right, so don't write this one, but here's another example that you could do very quickly. And what I want to do is do this in our calculator. So we've got the daily cost, C, in dollars of producing X items modeled by the function. So they're always going to give you some type of function. And then they're saying find the marginal cost, which is C prime. So marginal cost is kind of your difference in what it costs to produce versus what it costs to actually sell and make some money. But we want to find the marginal cost of this function, which is, don't write this one, but this is something you don't need a calculator for the first part. But what is it? They're basically saying find the derivative. And the derivative is just timesing by 2. So here's my derivative equation. However, what if I want to find the amount that it takes to produce one item? Well, that's the derivative by just plugging in 1. And you could go ahead and multiply it and do that by hand, but if you're allowed to use your calculator, let's try this again. All right, without a graph, let's do, now you don't have to plug it in Y1. You could if you want to. Let's say I don't want to here. All right, so what if I just go to a blank screen and I go math, option 8. All right, so then we're going to put X in the bottom. And then I want you to type in the equation exactly the way it looks, the original equation. All right. So it's basically what I'm telling the calculator to do is take the derivative of the function that was originally given. And that'll give me what C prime is. But now I want to find the cost at 1 unit. So that's where X is 1. And then just hit enter. And there it is. Our cost is $120.20. So it basically costs us 120. This is going to click over. So I'll come back to that calculator screen in a second. But what did I just do? I just found that the cost for creating one item is going to be $120.20. Now think of that. What if this was you were making a toy for Christmas, right? If you're going to produce one item, it's going to cost you $120. There's a strong chance that not many people are going to buy a toy for that price and you're going to lose your money. So it doesn't make sense to buy one item. But what about, is it more expensive to produce the 100th item or the 200th item? So let's look at the cost here and think, how much would it be for 100 items? Okay, so now here's the nice part. You just typed this in, go second, enter, and it has everything from the line before. And all you have to do now is click over and type in 100. So there you can see it's going to cost $140 for us to produce the 100th item. Okay, now let's check the 200th item. Go second, enter, and then all you have to do is change the 100 to a 200 and hit enter. Then you have all your information right there. Oops. Remember what we just found. We found the derivative, which is the change in cost per item. So this would be, the units are dollars per item. So if you're creating one additional, it costs 120. If you're creating 100 additional pieces, it's going to cost a little more. Dollars per item. And it's always important to think about the units after you take the derivative. It's your change in y's over the change in x's. Okay, so the goal there was just to get you guys used to using your calculator. It's not going to come up a ton, but when you can use it, we want you to take advantage of it. All right, so let's switch to what we're really doing today, and it's more with L'Hopital's rule. So I am going to have you write this one down. And I picked one that I know students would struggle with, not because of the calculus side, but it's more the pre-calculus side. And by the way, I am recording this. So if you, okay, so why did I pick a problem like this? Well, we're telling you you're going to use L'Hopital's rule, so you know that it's going to be 0 over 0 or infinity over infinity, but we still have to show all that work. And the one thing that I noticed when I checked the homework from before is students were not showing the very first piece. You have to evaluate the limit of the top, but you have to write the words limit. If you don't write the limit as secant goes to x, so if you skip this part right here, you're not going to receive full credit. And it's all because we have to be mathematically sound here. So now I want to evaluate what is secant of pi over 2. Okay, this is the reason why I'm doing this problem, so we can review more trigonometry. So I'm going to go over to pi over 2. And I know a couple things. I know that I go over 0 up 1, and I know that that's the cosine and the sine value. So I know what sine and cosine are, but what is secant? Well, secant is the same as 1 over cosine. That's the trig identity you need to know, the reciprocal relationship. And then what is cosine? Cosine is 0. So we actually end up with something kind of interesting here. We get 1 over 0, which does not exist. Okay, we don't like that, but I should also check the bottom now. So the top function is undefined, and the bottom function is most likely going to turn out to be something either a 0 or an infinity, something that isn't going to help us, but that undefined tells us this isn't going to work right now. Now we're going to take and evaluate the derivative of the denominator. So 1 plus tangent. Well, notice, what is tangent? Right? I know what sine and cosine are, but tangent is the same as sine over cosine. Now, if you've mastered the unit circle, you may already know this, but like I kind of tell you, I always rely on my Algebra 2 pre-calc skills instead of memorizing the unit circle. So, what is tangent to pi over 2? Tangent pi over 2 is the same as sine over cosine, and we know what sine is, and we know what cosine is at pi over 2. And notice we get that same divide by 0, which does not exist. So if I have two items that does not exist over does not exist, that means I'm going to try L'Hopital's rule. All right, so now that we do L'Hopital's rule, that means we're taking the derivative of the numerator. Well, the derivative of secant is secant tangent. And you could put a times here if you wanted to. It's secant times tangent. And the derivative of the denominator, while the derivative of 1 is 0, the derivative of tangent is secant squared. Okay, so derivative of the top, derivative of the bottom. But notice something interesting happens here. Algebraically, I have a secant factor on top and I've got 2 on bottom. So I'm going to reduce out the secant with 1 of the secants on bottom. And if you want, you can rewrite this just so it looks a little nicer. So what do I have? I have tangent over secant. All right, well, now I have to basically check these again. I have to check the numerator by itself. So I'm going to take the derivative of just tangent. Now here's the part where you can save some work. Sorry, I think I said derivative. We're checking the limit of the numerator. So we're just going to do tangent of x of pi over 2. Well, didn't we kind of already do that right here? So you know that the tangent of pi over 2 is going to turn into 1 over 0 doesn't exist, right? So you don't have to show any of this work because we did it once. And then I have to do the derivative of, or the limit of the bottom. Well, wait a minute, didn't we already do that as well? And the answer is yes. we ended up here with 1 over 0, which does not exist. So I cannot get an answer. It's undefined, but when I compare this, if it does not exist over does not exist, that is also kind of an indeterminate form. So what does that mean? That just means I need to apply L'Hopital's rule again and keep trying this out. Now we might notice a pattern here, or something might reduce out that's really helpful and friendly, and we could go from there. Now there is some other tricks you could do here at this point, and actually you could do some algebraic pieces that might reduce some things out, but if you don't realize that, I'm just going to do more L'Hopital's rule. So what do we have up top? We've got the derivative of tangent, which we knew was secant squared. And then I've got the derivative of secant, which was secant tangent. Isn't that kind of interesting? We basically have the same thing that we had before, but now the secants reduce out, and you know, probably picture what's going to happen here. I get secant x over tangent x, but isn't that going to result in the same thing we just had? It's just going to be flipped. Because if I take the derivative or the limit of secant, I'm going to get this bottom part down here. If I take the limit of tangent, it's going to just kind of keep going, and then I'm going to keep following in this pattern. So L'Hopital's rule doesn't always work 100% of the time, and that's what I wanted to show you is sometimes limits just don't exist, or sometimes there might be an algebraic trick. So there's no harm in kind of doing the work that we did because that discovered that maybe L'Hopital's rule is just not going to work for us. So here's what I'm going to do. I'm going to try one more approach. I'm going to say, wait a minute, isn't secant the same as 1 over cosine? And here's a hint. You could have done this right up here. But what about tangent? Isn't tangent the same as sine over cosine? All right, so we just used basically the reciprocal properties to write this. Some people call them trig identities. And then here's the interesting piece. I have a fraction divided by a fraction. So I'm going to rewrite this as 1 over cosine. And then instead of dividing by sine over cosine, I'm going to multiply by the reciprocal. Notice the benefit to doing that is the cosines go away. And I'm left with 1 over sine, which now this is either going to give us our answer or it's going to tell us it's undefined. So what did I do? I rewrote secant as 1 over cosine. I rewrote tangent as sine over cosine. And then I had a fraction divided by a fraction, so I just changed it to the numerator times the reciprocal of the denominator. That reduced the cosines out, and then I have a new limit. And this limit can then be evaluated at pi over 2. So I'm going to plug in pi over 2 and see what is sine of pi over 2, which I have right up here. We know that sine of pi over 2 is 1. And after all that work, my answer was 1. Okay, So we are still doing L'Hopital's rule, and that kind of gives you a hint at which route we're going to approach. But what I'd like you to do is go ahead and just write down this limit. And you'll notice as you're writing it, we don't know what the function f is. But we do know that f and its derivative are given in the table here. So when we do our work, we're going to have to look for what is f of a number. And that is displayed in this table. And then we're going to have to look for f prime of a number as well. So we always refer to the table there. All right. So what we're gonna do is take the numerator, and we're just going to evaluate that as x goes to 2. That's really quick because that's just a number. We don't even need the table for that. Right? And you can do that all in your head. 2 times 2 is 4. 4 minus 4 is 0. You don't need to show any work there, but you can see the numerator goes to 0. And then we're going to evaluate the denominator. We're going to evaluate that when x goes to 2. All right, so this is just substitution. And again, you can show as little or as much work as you need for this piece. But when I plug 2 in, I end up with f of 6. So I got to figure out when x is 6, what is f of 6? That's equal to 2. Basically, finding the intersection of f and 6. All right, so notice what do we get? We get 0 over 0. Just have a frowny face. We don't like that. That is our indeterminate form. I'll give you guys a second to get caught up here. All right, so now when I apply L'Hopital's rule, we have to use all the derivative rules that we need to use here. So we get 2x minus 4. The derivative of 2x minus 4 is just 2. And then on the bottom, this is the part where a lot of kids make a mistake. We're taking the derivative of f of 3x. Notice 3x is on the inside. There's a chain rule here. So I'm going to take the derivative of the outside, which is f prime. We're going to keep the inside, and then I have to multiply by the derivative of the inside, which is 3. That is the number one mistake on this problem, is students just forget that we have to apply the chain rule. All right, and then notice the derivative of the negative 2 goes away. And here's a hint. Most likely, L'Hopital's rule is going to work here because there's nothing fancy about the numerator. So I'm going to now be fairly confident I can say equals because I know that this top part is not going to turn into 0 or infinity. But then the bottom, we got to plug in 2. And notice how I'm not writing the word limit either, because I'm using the 2 and plugging it in. So then I get f prime of 6. All right, well, where is f prime of 6? That's equal to 4. We get 4 times 3 over 2, which is 2/12 or 1/6. I have a very strong feeling that the AP test is going to lean more towards this type of problem where they just use f or g or functions instead of more derivatives like we saw in the other example with secant over tangent. This is harder to find the answer on or to cheat from if you're taking the AP test from a computer, just so you know. All right, let's try. I think we got one more problem that we'll do. And notice the table gave us the points, right? And then it gave us the slopes at those values. Well, points and slopes can also be determined from a graph. And that's what this piece is right here. So resize this. I'm going to give you a very brief amount of time to draw this picture. Okay, so let's go over this one. If you're watching this video, pause it and just analyze the graph. But we found the slopes of each piece of these linear items just by doing rise over run. Remember, slope is the same as derivative. So now I want to evaluate the limit. And black. The limit as x goes to 0. Now I'm going to try to save myself some space because I know that I have to check the limit of the first one. So I'm just going to write this part, and we're going to just test plugging in 0. So I'm basically just going to put 0 into the numerator. I do have to show that I'm testing only the numerator limit. So you're putting the limit here. And then we just need to simplify. F of 0. So I have to figure out what is f of 0. That's just a point, right? F of 0 is a location. So I know that at when x is 0, f of 0 is 0, which means this whole thing just turns into 0. So the numerator, the limit of the numerator went to 0. Now I'm going to check the limit of the denominator, which even though I know you probably could just plug in 0 in your head and get the answer, you still have to write the limit of the denominator. Right? You have to write that notation. Then you could just say 0. You don't have to show this work here. But when I compare, I end up with the indeterminate form, 0 over 0. So now I have to take the original function and we're going to apply L'Hopital's rule to the original piece. Don't forget about the chain rule here. So if I take the derivative of the top, this 2 out in front is just a multiplier, so it's going to kind of stay. I'm going to take the derivative of f, which is f prime. We're going to keep the middle, or the inside, but then I have to do the chain rule. So I have the derivative of 2. And then I actually have to take the derivative of the second piece. The derivative of 2x is just 2. Right? And then we're going to take the derivative of the bottom, which is just product power rules. Derivative of 4x is 4. Derivative of 4x squared is 8x. And you mentally could kind of plug in 0 on the bottom and realize you're going to get a number. And we kind of already have an idea that if I have a number, it doesn't matter what the top is going to be. So I can confidently put equals here and not have to check each limit separately. And you could simplify before you write all this, but we're just going to plug in 0 for x here and here. And notice this part right here is going to turn into, we need the slope at 0. I need the slope of the point at 0. Well, f prime of 0 is the red slope. So that's a -2 right there. And again, you don't need to show all of this work. But I know that, oops, f prime of 0 is -2. And then I get -2 times -4 is it's -4 times 2 is -8, plus 2 is -6. -6 over 4 tells me the limit is -3/2. All right, so notice the style of this. It's the same as if they gave you a table. The only difference is you have to read your points and you have to identify what's the location of a point or what's the slope, which is the same as the derivative at a point. And it's always going to be a linear equation because that's the only thing we can actually calculate slope from, rise over run. So that's as hard as it gets right here. All right. I think we're gonna skip these two problems because we only have a couple minutes left. This one was a free response question, and it looked a little crazy, but notice this notation here is the same as what we just did. So if I ask you to just find the limit, you're gonna plug in 0. You already know what the 0 is, and you can simplify that and then use L'Hopital's rule. So we don't need to do that one. And this one was just a little more crazier one. I think I'm going to do, actually, I think on Wednesday, I'm going to do these two problems just as a small video. So your homework tonight is 4.4 day 2. It's in Delta Math. And what I'd like you to do is submit your handwritten work. Okay, so submit your handwritten work to this because I want to see that you're following L'Hopital's rule. And it's only, I think it's 6 problems. I think 3 of them are tables and 3 of them are graphs, just like we went over. So good luck. I will be available from 1 to 2 in my office hours. Please stop in if you have calculator questions or if you have any questions overall.